Hello, BNG319 class. Hopefully you're all having a good week this week without any physical BNG319 class to go to. You found some good way to use that time. So this is our recorded class where we're starting our organic chemistry portion of BNG319. So the review is over. And now we're heading on to organic. And we're going to talk about some organic chemistry reactions in this lecture here. Okay, so first we've gone over some of the compounds that you will run into when we're doing organic chemistry. So let's review some of these compounds. First we'll start with these aliphatic compounds. And they are the alkanes, alkenes, and alkynes. What's up with alkanes? Well, they only have single carbon-carbon bonds, no double or triple bonds. And some good examples are octane, found in gasoline, propane, found in your gas grill. Alkenes contain one or more double bonds, things like ethylene, carbon-carbon double bonds, that is, ethylene and the like. Alkynes contain one or more carbon-carbon triple bonds. And these are, a good example of that is acetylene. So alkanes do not contain double or triple bonds. So we call that saturated. We call these types of alkanes saturated hydrocarbons. And that means all carbons in the molecule are saturated with hydrogens. So this octane molecule here is saturated with hydrogens. Alkenes and alkynes have the double triple bonds respectively. These are both unsaturated hydrocarbons. They're unsaturated. They could have more hydrogens, but they don't. Instead they have a double carbon-carbon double bond in the case of ethylene and a carbon-carbon triple bond in the case of acetylene. And there is a certain geometry that occurs when we're talking about the different bonds. Single bonds in organic molecules are unconstrained and can rotate pretty freely around their bonds. Double bonds are constrained because of the fact that they are double bonds. So if you have one of those old organic chemistry molecule making modeling sets and you try to make a double bond, you notice you can't twist that double bond around. It basically is constrained to stay where it is, where some of the molecule is going to be on one end versus the other, and we'll get into what that means. Right now, some of these alkenes can form what are known as cis or trans isomers. So if we're talking cis isomers, we look at relative to the double bond. With cis isomers, carbons are on the same side of the double bond, and we'll illustrate that in just one slide from now. Trans double bonds, we have carbons on different sides relative to the double bond. And this becomes especially important when we talk about fats, when we get into our special molecules talking about fats. The cis and trans alkenes are geometric isomers. That's what they are. And we'll look at some geometric isomers right now. So we have here cis-2-butene. And what do I mean by cis? Well, I said, the carbon skeleton is on the same side relative to the double bond. And that means, so we have on one end here, we have a CH3, and then we have a hydrogen. So the CH3 is facing below the double bond if we're just looking at it on the paper here. Same on the other end of butene. Again, we have a CH3. That CH3 is facing down, the same as this CH3, so that is cis, because they're both on the same side of the alkene here, and we have hydrogens up top. It becomes trans if one of the CH3s is above relative to the double bond. So one is below and one is above. Here we can see in trans-2-butene. Same with pentene. Here we have CH3, CH2, CH3. Both are on the bottom relative to the double bond. So that's cis 2-pentene We have 1 on the top here, CH3 is on the top, CH2, CH3 is on the bottom. That means it's trans, so this is trans 2-pentene. And here we have 2-methyl-2-butene. Can it be called cis or trans? No, it cannot. Why can't it? Well, here we have CH3s coming off both of the bonds in this carbon here that are attached to the double bond of the other carbon. So you have a CH3 here and a CH3 here. Same with here, CH3, CH3. And we can have this CH3 on the bottom or the top, but we can't really say cis or trans because there's always going to be a CH3 here. So this would always be cis, this would always be trans, and this would always be cis, and this would always be trans. So because we have symmetry on this carbon here, this is neither cis nor trans. It's simply 2-methyl-2-butene, regardless of which way this CH3 is facing. So here in these two examples in A and C, we have cis and trans, but here in B, we don't have cis and trans here. Again, another review of aromatics. These are molecules that have multiple conjugated double bonds. They're very stable molecules, and they're cyclic. So they form kind of a circle here, like benzene, right here. And these are so named because many of these compounds had a sweet or pleasant or aromatic odor. These are aromatic compounds here, like benzene, phenol, tyrosine, the amino acid tyrosine here. And so these have, like phenols, have an OH group attached directly to the aromatic ring. And so here, this is methylbenzene attached with a CH3 attached to the aromatic ring here. Functional groups have 6 carbons on which they could attach here. You see how they can attach here, here, position 1, position 2, 3, 4, 5, all the way to 6. And so we can have many different configurations here where the top is always 1, so this is methylbenzene or toluene. Here we have 1,2-dimethylbenzene, so this is 1, this is 2-dimethylbenzene. 1,3-dimethylbenzene here. And so this is O-xylene and this is M-xylene. More as to what O and M mean later on. This is ortho and this is meta. But what does that signify? Alcohols are carbon-containing molecules with the hydroxyl group attached. So an OH. And these are bound to a saturated carbon atom, like ethanol here. This is a saturated carbon atom here in butanol as well, with the OHs attached. So like ethanol is a common, the most common alcohol. Isobutanol and butanol, these are fairly well-known alcohols here. Carboxylic acids contain the carboxyl group here. This is what the carboxyl group looks like. We have what's called the carbonyl, the C double bond O here. Attached here to the carbon is also an OH. And that is the carboxyl group. They're very common, very abundant. Like I said, fatty acids are carboxylic acids. Acetic acid is fairly common. And if we have a salt of the carboxylic acid, it's called carboxylates. So sodium acetate is a carboxylate right here. What you should also know about carboxylic acids is that they can form hydrogen bonds with one another. So in fact, one part of the molecule can be a hydrogen bond donor, where the OH is here, there's a hydrogen bond donor, and one part can be the hydrogen bond acceptor, this double bond O here. And we can see two hydrogen bonds made by these two acetic acid molecules. Aldehydes, ketones also contain that carbonyl group. In aldehydes, the carbonyl is on the end of the carbon skeleton, so that's known as the aldehyde group, and that's that functional group. So like formaldehyde is a common aldehyde. Ketones contain a carbonyl group not at the end of the carbon skeleton, but somewhere in the middle. They're not as reactive as aldehydes are. Things like acetone are common as a common ketone. Esters, we talked a little bit about hydrolysis of esters. Esters are derived from acids. The hydroxyl group gets replaced by an alkyl group, so we have an alcohol like ethanol and acetic acid. So basically the OH group in the acetic acid is kicked off, and we get the alkyl group from ethanol, and we make ethyl acetate. And it's usually esters are formed like this as a reaction between an acid and an alcohol. And here's an example, ethyl acetate, which is a common one. Amines, we haven't really talked about amines much yet, but we will. Amines have a nitrogen attached to an aliphatic or an aromatic carbon chain. So we can have different kinds of amines depending on where they're located. A primary amine is a nitrogen that's attached to one carbon. Secondary amine has a nitrogen attached to two carbons, and a tertiary amine has a nitrogen that is attached to three carbons. And we can see this here in this chart. A primary amine like ethanamine or ethylamine. Here we have a nitrogen group attached to one carbon. N-methyl-1-propanamine or methylpropylamine is a secondary amine. We can see we have the nitrogen is attached to 2 carbons. Tertiary amine, the nitrogen is attached to 3 carbons, and that is sec-butyl dimethylamine or NN-dimethyl-2-butanamine. We could also have a tetraethylammonium ion, a quaternary ammonium ion, but because we have an extra bond to the nitrogen, you notice nitrogen is typically only bonded to 3 things at all time. But if we try to add another carbon chain, we end up getting an ammonium ion of sorts. In this case, this is tetraethylammonium ion, as you can see right here, and that's a quaternary ammonium ion. The nitrogen is bonded to 3 different carbons. And we will encounter more functional groups in our survey of organic chemistry, things like thiols, amines, ethers, things like that. And of course, we will discuss these things in more detail as needed. And these groups are important because they tend to be the locations where reactions are going to happen. Organic reactions are going to happen. All right. So, if we think about it, alcohol biofuels have been well studied in recent years, even ethanol, things like ethanol, butanol, isobutanol, and the like. So if I'm running 2 fermentations, both microorganisms are making an alcohol, C4H9OH. The 2 products are different molecules, though, but they have the same chemical formula. How is this possible? So this is possible because the 2 alcohols that are being made are actually isomers. They have the same chemical formula, basically, but they are butanol, or N-butanol, or normal butanol, which looks like this, and isobutanol, which looks like this. You can see they're the same amount of oxygens, carbons, hydrogens, but they have a different structure. They have different properties because they have different structure. And this is very common. And this is why we can't just typically write our organic compounds like this. Because how do I know if we're talking about butanol versus isobutanol? And it gets even more complicated the longer the carbon chain is. So we definitely try not to do that. We much prefer the Lewis structure with or without showing the free electrons. But we usually prefer this kind of Lewis structure here in order to write our organic compounds. So we talked briefly on Thursday about catalysts. You know, we know how catalysts work somewhat, or we have an idea of what they do, but how does it do it? How does a catalyst decrease the activation energy? We know catalysts will take, reactants to products, and if you don't have a catalyst, you have a certain activation energy, which is going to be a lot larger than if the catalyst was present. It significantly reduces that activation energy, making the making the reaction happen a lot quicker. And we'll talk more about this when we get into catalysts. We will have a whole lecture on catalysts. But in the short term, it's easy enough to know that what a catalyst does is it stabilizes the transition state. So the transition state from reactants to products. So if you can imagine, this is kind of a pathway here, this chart, where reactants go on a long journey from reactants to products. What a catalyst does is it stabilizes that transition state, giving it a kind of a shorter way to go from reactants to products here. Okay, so what have we talked about so far in this class? Up to now we've talked mostly about stable molecules. But now we're going to talk about some unstable molecules and how they react. Because to react is to be an unstable molecule, or vice versa. The textbook is largely descriptive about this, and it gives you kind of a good framework as to what to expect. As this lecture here will give you a good framework to explain and even predict the reactivity of organic molecules. So hopefully by the end of these two lectures you'll be able to do that. And if you cannot, you need to let me know that you cannot, so we can go over these things in greater detail. Okay, which of these molecules is more reactive? We have the chloride ion, or actually the chloride radical here, and we have a chlorine atom, basically, a dichlorine atom. Well, unpaired electrons are extremely reactive, like this one. So thus, which is more reactive? The answer is this chloride here. This chloride, I assume, is a radical here. And I assume that because now I'm going to start talking about free radicals. A free radical is an uncharged molecule. So, you initially see chloride, you would expect there to be a charge there for chloride ion. But this is a chloride radical because it is an uncharged molecule having an unpaired valence electron, again, like our chloride molecule there. They're unstable, they're highly reactive. When free radicals occur, they want to react with something. Doesn't really matter what. And there are organic reactions that can happen. They can be started by free radicals. And so, in organic reactions in general, we're talking about reactions that proceed by intermediates. Up to now, we really weren't talking too much about that, about intermediate steps. And you'll be able to visualize some of these intermediates in future classes here. In many cases, we can even examine the detailed mechanism of a reaction. So basically the flow of electrons from reactant to intermediate, to whatever intermediates are present, to the product. And the chemical equation will show you the reactants and the products. Our mechanism will show you the steps. And we'll get into the mechanisms later. But for now, it's enough to familiarize ourselves with reactants and products. Back to radicals. And so we don't think of radicals necessarily as having a ordered stability, or some being more stable than others. But in the case of reactions, more highly substituted radicals are more stable. What do I mean by that? So when I'm looking at this methyl radical here, if I have only hydrogens bonded to this carbon and a free electron, an unpaired electron, that is much less stable than if I have one methyl group, less stable than if I have two methyl groups, and even less stable still than if I have three methyl groups. So what the substituted means, highly substituted, means the hydrogens are substituted by carbon chains or methyls or ethyls or whatever. And we can use this stability to predict reactions, to predict what they're going to do. And so we can predict reactions, which means we can predict the major product. Okay, so we have an alkane, we have propane here, and we have chlorine and light as the initiator here. Are we going to get this or this more? And same with bromine. Are we going to get this bromide or this bromide as our major product? Well, how do we know what the heck's going on? Well, we got to look at how these reactions proceed. So we look at the mechanism of radical reactions. So you noticed here in this simple equation here, you notice that part of the reaction involves chlorine or bromine. They involved a halogen. And so the halogen and the light, what the light does is it takes these halogens and basically breaks this bond and gives us two halide radicals. And these are reactive, and they want to react with something. And look, here we got some propane. So basically what's going to happen is the chloride radical here is going to react with the propane here to form a propane radical plus hydrochloric acid. So it'll either do that in the middle carbon or it'll do that at the end here. And so the question is, which will it prefer? Which will be our major product is dictated by whether the propagation occurs like this, the top, or like this, the bottom, more frequently. And so you can see propagation where we get the propane radical, and this will create more chloride radicals until eventually we get the alkyl chloride plus another chloride radical, and then termination would occur when chloride radicals start to react with each other, reforming that Cl2 and ending the reaction. But do we end up with more of this or more of the compound that has chlorine on the end of the compound? And the answer is in here. The more highly substituted is more stable. And so it'll be around long enough to give us a reaction here. So this is the more stable here. This is the highly substituted carbon, or the more highly substituted carbon. So you can see it's got two carbon-carbon bonds instead of the ones at the end, which only have one. That's where the reaction is going to occur most often. So you're going to have this product be your major product. Okay, so we can guess the product here. We can examine the products of this monohalogenation reaction and identify the major product. So what could we get here? We could either get a chlorine on the end here. This is a methyl group here, chlorine on the end. Or we could get a chlorine in the center here. And the answer to the question is, well, the reaction, this is the more highly substituted, the more stable. It's going to be around long enough to react. That is the major product. This will be made, but it is the minor product. So because this carbon is attached to three other carbons, this methyl group, this methyl group, this methyl group, this is the major product. Okay, radical reactions. Really the only significant reactions of alkanes are the radical reactions. And combustion is actually a radical reaction, although we won't get into that too much. More than we already have anyway. Polymerizations are often radical reactions. And again, these happen in alkanes. Polymerization of alkanes like polypropylene, for example. We'll talk more about those types of reactions later. There are lots of radical reactions in biology. superoxide radical is released by immune cells to kill foreign cells. DNA will react readily with radicals, leading to mutations. There's a lot of business about nutraceuticals and antioxidants that will supposedly fight free radicals for you. And in fact, they do. They're very useful in basically absorbing free radicals. So these antioxidants are molecules that can react with free radicals to form less reactive radical molecules. For example, we have vitamin C here. Vitamin C will pick up a radical. A radical would react with it. It'll become radicalized itself, but it is much less reactive than some radicals that could also be formed, like in your DNA or elsewhere. Okay. Now what if we were looking at reactions with electron pairs? So we'll see these two in organic compounds. The simplest types of ones we'll see are the single replacement experiments, where we have, essentially here we have an iodide and chloride, kind of switching places here. So we got sodium iodide plus methyl chloride gives us methyl iodide plus sodium chloride. So essentially what will happen is there'll be an electron donation from the iodide to the carbon here, where the halogen is, where this chloride is. This will in turn donate electrons to the chlorine, and the chloride will then become a chloride ion and pair up with the sodium to make sodium chloride. Okay, so what's going on here? There's a donation and there's an acceptance of electrons. So what do we have? Well, we have a nucleophile, and a nucleophile is an electron-rich atom or group of atoms that donates a pair of electrons to form a new covalent bond. And we also have an electrophile. An electrophile is an electron-deficient atom, or group of atoms again, that accepts a pair of electrons to form a new covalent bond there. Okay, so what are the nucleophiles? So here's some examples of nucleophiles. These are the electron donators. And you can see that a lot of these are negative, so not surprising that they might be electron donators in this case. The halides, like fluoride, chloride, bromide, and iodide. And of course we saw that here with iodide acting as the electrophile. Oxygen in the OH of alcohol perhaps, or just the OH of a base. A alkyl oxide here. Sulfur, sulfhydryl, and the sulfalkyl, alkyl sulfide or whatever. These are good nucleophiles. Nitrogen, with its free electron pair right there, is a good nucleophile. These are all good electron donators, including alkenes. The double bonds there make a great nucleophile. Electrophiles, or electron acceptors, are carbon atoms that are connected to halides, because the halide is really trying to pull away those electrons. So the carbon is willing to accept electrons from another source. And the carbonyl carbon, the COO, the carbon here, here, and here. These are great electron acceptors, or electrophiles. Okay, so what do we got? Nucleophile or electrophile? Let's take a look back at this reaction here. We've got sodium iodide and methyl chloride. The nucleophile, as I said before, is iodine. This is the one that's donating electrons, as you can see by this arrow here. The electrophile is this carbon. It's accepting those electrons. And the chloride gets a special name called the leaving group, because in this molecule, chloride is leaving and iodine is taking its place. So we've got a nucleophile, an electrophile, and a leaving group. Okay, let's take a look at this reaction below here. Which would be the nucleophile? The bromide radical or this bromine right here? That is a nucleophile. Okay, let's talk about amines as organic bases. Things like ammonia, those make good bases. And in fact, this is a good way to look at nucleophiles and electrophiles. It's the simplest example of nucleophilicity, the abstraction of a proton. So we have an electron pair donor here, donating grabbing a hydrogen and making an ammonium ion. And here we have the hydroxide ion. And so a good practice to do is to write the mechanism of the reverse reactions here. So we see the electron pair being donated to the hydrogen here. The hydrogen is donating the electrons back to the oxygen to give us the two ions. Okay, so let's look at hydration of alkenes. Where double bonds, like we said, double bonds can act as nucleophiles. So what they can do is donate electrons to grab a hydrogen and become a alkyl ion here, a positively charged ion. And we have water. We're starting with base here. And then what will happen is this oxygen will then donate electrons to form this intermediate, this charged intermediate here. Again, we get the water coming to grab a hydrogen, reforming that acid, and now we have an alcohol. So these are carbocation reactions, and we can use the same rules for stability of carbocations as we did for the stability of those radicals. So again, the more highly substituted cations are more stable. So this CH3 ion is less stable than this ion here, which again is more highly substituted with the hydrogens being substituted for methyl, in this case methyl groups. And again, we can use this like we did before to predict reactions. Except now this has a fancy name to it. It's called Markovnikov's rule. And basically, it allows you to predict the reaction for these carbocation reactions. So essentially what you're doing is you're counting the number of hydrogens attached to each carbon atom involved in the double bond. So this or this, because we know this is going to be a hydration reaction of a double bond. So the carbon on the right here has more hydrogen atoms, 2 of them to be precise, attached compared to the carbon on the left, which has none. Now Markovnikov's rule predicts that the hydrogen will attach to the right side of the double bond and the OH to the left side. Again, it's basically what Markovnikov's rule is this. The more highly substituted cations are more stable. So when we make that carbocation right here, we're going to get the OH from the water attaching to this carbon that right now has no hydrogen atoms attached. So that's what we're going to see. This is going to be the major product of this reaction, of this hydration reaction here. So, and again, we can follow the mechanism of the hydration of asymmetric alkenes and ask ourselves the question, well, which is the major product? Is it going to be this alcohol or this alcohol? And we follow the mechanism and see first the donation of electrons to the acid to get the hydrogen. We make our carbocation. Water will react here or here. And what we see is that we get the more highly substituted alcohol here, because the more highly substituted carbocation is more stable. And so with that we can predict this reaction here. So we have this alkene plus water, and we're going to see compound A, we're going to see compound B, are we going to see compound C, or are we going to see compound D? Well, first of all, we can eliminate compound C and D right away, because where the hydration is going to happen is going to be the double bond here, the hydration of the alkene. So it'll either be here, this carbon, or this carbon, which is either A or B here. So the question is what is it, A or B? So again, we go back, we think to ourselves, which of these two carbons is more substituted? And whichever that is going to get the hydroxide, the hydroxyl group added to it. So that essentially rules out B and tells us that A here is the right answer. That is going to be the major product of the below reaction here. Okay. And we also, when we're thinking about organic compounds, we have to think about the conformations. Conformations have the same molecular formula. They have the same atomic connections, but they have different three-dimensional shapes. And you can see example of different conformations of butane right here. They're all interchanged by the rotation of single bonds. Constitutional isomers, again, molecules with the same molecular formula, but different atomic connections. And so we already talked about some of these. Here's an example. These are all C6. These are all C6 molecules anyway, and they all have the same number of hydrogens. But we've got hexane, 2-methylpentane, 3-methylpentane, 2,2-dimethylbutane, 2,3-dimethylbutane. Again, same molecular formula. If we were just looking at the molecular formula, we would not know which one we were dealing with. It's the atomic connections that tell us what the molecule is. And each of these compounds will exhibit different behavior depending on what you're using them for. So it's important to write out your constitutional isomers. Stereoisomers have the same molecular formula, they have the same atomic connections, but they have different three-dimensional shapes. You know, we've already talked about this a little bit, but it's not from bond rotation like with these conformations here. These are stereoisomers. So again, for an example, we have, you know, the cis and trans 2-butene here. Here's another one, 1,2-dimethylcyclopentane. We see cis has 2 methyl groups pointing out of the screen. Trans has 1 methyl group pointing out of the screen, the other methyl group theoretically pointing into the screen. And we will deal with a lot of these things in much more detail as we go along. Okay. So we can think about naming, and we're not going to spend a lot of time, and I'm certainly not going to quiz you on the naming of compounds. You can look up the names of compounds in a book. I want you to be able to recognize certain functional groups, recognize certain reactions, and predicting outcomes. That's really what we want to focus on here, not naming. So the prefix for a lot of organic compounds depends on the number of carbon atoms. So we have 2 carbon atoms. We'd use ETH, F, as in ethanol or ethylene. And if we have a different type of molecule class, you know, things like propane, alkanes is ane, would be the suffix. Alcohols, we have, again, ethanol, butanol, things like that. Carboxylic acid. We have things like hexanoic acid. Amines, methylamine is common. Aldehydes, propanal, ketones, octanone, etc., etc., etc. We can go on all day with different permutations of different names. So again, let's name these molecules here. CH4, this is methane. It's an alkane, obviously it's an alkane. This is carbon-carbon double bond here. This is ethene or ethylene. This is a 3-carbon CC triple bond here. Propyne, or this is 2-butanol. So you can see this is 1, 2, 3, 4 carbons with an alcohol group. This is butanol, and because it's on the 1 second carbon of the butane molecule, it's butanol, 2-butanol. Pentanoic acid, 1, 2, 3, 4, 5 carbons. Pentanoic acid. Okay, so we've talked about hydrolysis of esters. Let's talk now about preparing of esters. A reaction that has a carboxylic acid and an alcohol will produce an ester. So we can see a few examples of that here, where we have an alcohol and a carboxylic acid, and what happens is we kick out a water as part of the product, but we end up also with an ester here. So you can see what makes up the ester molecule here in black. So we lose that water, but here we have this ester. And it doesn't matter what's on the other side of the carbonyl, as you can clearly see, or what's on the or what's attached to the alcohol. You will make the ester here, and many different kinds of esters can be made. But in all cases, you're kicking out water as another product. So the preparation of esters is a condensation, because along with the reaction, water is coming out. So it's a condensation reaction, and water is our other product here. As you can see, in every single ester condensation, water is the second product. Okay, so again, here's the mechanism. Here's what this would look like. We have methanol here, and we have acetic acid here. And so in the presence of an acid or base, we will produce an ester. So essentially what happens is that we make a negatively charged ion out of the methanol, which we have 2 electron pair here, is going to donate to the electrophile carbon here in this carbonyl group. We get this intermediate molecule, and again, we lose the double bond. We have the electron pair from this oxygen will donate to this double bond, and this bond will kick off our hydroxyl, and then we end up with this ester here. So we lose this OH, we reform the double bond, the carbon double bond, to the oxygen, and get our ester. And so that is the mechanism of ester formation. Okay, so in this ester formation, what is the missing reactant in the below reaction? Okay, so we have our acid here, whatever this carboxylic acid, 1, 2, 3, 4, this is butanoic acid. And so what is our other molecule? Well, it's got to be an alcohol, and this is an alkane, so that rules A out. It's not A. This, don't really know what this is. I don't think this is much of anything. There's nothing that just ends in an oxygen. So this gets ruled out, D. This is another acid. We have an acid already. We need an alcohol. We don't need B. Process of elimination gives us C, the only alcohol here, as the missing reactant in the below reaction. Again, the ester is the product. Yep, it's the alcohol. So the acid and this alcohol will give us this ester right here. Now let's talk about reactions with amines. So amines can accept protons from water and from acids. So for methylamine, we can make methyl ammonium ion. Methylamine and hydrochloric acid will give us methyl ammonium chloride. And with reactions of amines to acids, we can produce amides, so organic acids. So amines react with carboxylic acids to form amides. The mechanism is the same for making esters, and the reverse reaction is hydrolysis. So here we are. Here we have, again, acetic acid and methylamine will give us this amide here. So here we can see a couple of examples of amides, where we have one part is carboxylic acid, and this comes from the ammonia, and this is an amine, another carboxylic acid residue. So these are amides. So here we go. Reactions to make and unmake amides. So right here, we have the reaction of the carboxylic acid with ammonia. We make this Zwitter ion here, which has a negative and a positive charge. But then we kick out water in what is indeed a condensation to create this amide. Same here, if we have methylamine and not just ammonia, we make an intermediate here that has a negative and a positive charge. And with heat, we again kick out that water, we do some condensation and make the amide. Now if we have amides, we can take water and hydrolyze them. So with acid and heat and water, we can take this amide and turn it into ammonium and acetic acid, this amide into ethylamine and again acetic acid, if we add water, acid, and heat. Okay, so again, what is the product of this reaction? So it looks like we're going to make an amide here. And we have this amine, we have this acid. So this doesn't have a nitrogen in it, so this can't possibly, this looks like an ester. So choice A is right out. I don't know what this is. This doesn't look likely to happen. C double bond N, at least not with these reactants. So that's out. Same here. I don't even know where the oxygens went. That's out. So by process of elimination, we have item C here, which has the carbonyl, it has the NH, and looks a lot like what we would expect an amide to look like. So the answer is yes. It is part C. Okay, so the summary of this first part: organic reactions fall into two categories. There are reactions with unpaired electrons. Usually they require light or heat to get started. These are radical reactions. Halogenation is a good example of those. And there are reactions with electron pairs, which is overwhelmingly most of the reactions we'll deal with in the organic chemistry portion of this class. We have nucleophiles, which are electron rich. Their negative charges help, like in the halides. Electrophiles are electron deficient. They're atoms that are connected to electronegative atoms, so they are feeling electron deficient. Most complex organic reactions are a series of simple reactions between these nucleophiles and these electrophiles. Okay, so you want to learn more about this stuff, and I know you do because we're going to have a quiz on it. Read in the Reynolds book, Chapter 8, pages 276 to 319. If you have questions about it, please let me know. You can send me an email if everything is just completely confusing. I'll do my best to help you. When I get back from being away in October, we need to discuss whether we want to do a voluntary recitation session. I ran this last year. It was very successful and very helpful for students. I'd like to do it again this year. I'd like to offer it at least again this year for people that want to ask more questions but don't have the time or need to synthesize on their own before they ask questions. So we can do some kind of recitation session on maybe a Monday before the quiz or the Friday after the Thursday class. So we can talk about that and find out when people's availability is. Homework number 1, which is all our review from Gen Chem. That homework is due next Tuesday, the 3rd, at the end of class. And I will post the second part of the organic reactions chapter or chapters soon. You'll have it definitely by Thursday. And then we will have a little assignment that'll be due when I get back.